Section 2.4, modeling motion with matrices. We're going to start with a vocabulary term, a vertex matrix. It's a 2 by n, and n can change, be used to express the vertices of an n-gon, whether it's a pentagon or a hexagon or a octagon, whatever it might be. This is just kind of a general term for any number of sides polygon. Okay, so in this vertex matrix, the first row are your x coordinates, the second row are your y coordinates. So if I had a polygon, in this case would be a triangle ABC with vertices at -2, 4, 0, 6, and 1, -1. What this would look like, the vertex matrix would be this. We'd have -2, 0, and 1, our x coordinates. Here, -2, 0, and 1 become our first row, and then our second row become our y coordinates. So 4, 6, -1. So each pair vertically, -2, 4, 0, 6, 1, -1. That makes up our vertex matrix. And that's what we're going to be starting with all of these examples here, okay? So we're going to start with this vertex matrix, and then we're going to transform it based on the type of transformation we want to make. The first type of transformation, just like when we talked about in Algebra 2, is translations. Whoops, let me go back to the pen. It's a translation matrix. Remember, translation is a shift or a slide. The translation with matrices is exactly the same thing. The translation matrix is a matrix added to a vertex matrix to translate an image. Okay, in the translation matrix, all the elements in each row are the same number. So all of these are going to be the same. All of these are going to be the same. They don't have to be the same this way. You could have 2s and 5s, but they're all 2s and all 5s, or all 7s and all 0s, something like that. Okay. With this, all directions are normal. Remember, when we're talking about transforming functions, the horizontal translations were always backward. If we wanted to go right, we had to subtract. If we wanted to go left, we had to add. In this case, everything is normal. Up and right are both positive numbers. Down and left are negative numbers. So if we want to go to the right, these will be positive. If we want to go left, these will be negative. Positives here for the y's will give you up, and then negative for the y's will give you down. Okay? If the original image is labeled ABC, so like this one right here, the new image is labeled, and this is pronounced A prime, B prime, C prime. Okay, every one of them has the apostrophe. The apostrophe represents prime. Okay, just a little heads up, because we'll be using that here in a little bit. So I've got an example here. Suppose quadrilateral RSTU, quad means 4, so we got a 4-sided figure with vertices R, S, T, and U is translated 2 units right and 3 units down. Okay, I'm not going to read off all the ordered pairs. You can read them for yourself. So number 1, represent RSTU as a matrix. So we're going to make the vertex matrix first. I would make this in the order that it's listed. If it's named RSTU, we'll list them RSTU. Okay, so we'll have our R coordinate first, 3, and then 2, and then S is next, so that's 7, 4, and then T is 9, 8, and U is 5, 6, and there is our vertex matrix. There's the answer for number 1. Number 2 then says the translation matrix, right? The translation matrix. Now, if we have a 2 by 4 vertex matrix, our translation matrix is going to be exactly the same size. Okay, we're going to have the exact same dimensions. So we'll need a 2 by 4. Now remember, with the translation matrix, these 4 numbers in the first row are going to be the same. The second 4 numbers in the second row are all going to be the same. We need to determine what that's going to be. So if we're going 2 units right, so if we think about the number line, 2 units right means we're getting bigger. So our x values, or our first row, is all going to be 2s, 2, 2, 2, and 2. And then 3 units down for the y's. Down is a negative change, so these are going to be -3. So -3, -3, -3, and -3. So now question number 3 then says find the vertices of R prime, S prime, T prime, U prime. Okay, so what we're going to do is we're going to take our original vertex matrix. So I'm going to rewrite this one more time. 3, 2, 7, 4, 9, 8, 5, 6. And what we're going to do is we are going to add our translation matrix. Okay, so we'll have 2, -3, 2, -3, whoops, 2, -3, and 2, don't need a fraction bar, -3. And we're going to add these 2 matrices together, and that will give us our vertices of R prime, S prime, T prime, and U prime. So let me draw this in here. So we got 3 plus 2 for the first one. That's a 5. We're just adding 2 to all the x values. So 7 plus 2 is 9. 9 plus 2 is 11. 5 plus 2 is 7. and then we'll do the same thing for the y's. 2 minus 3 is -1, 4 minus 3, or 4 plus -3 is +1, 8 minus 3 is 5, and 6 minus 3 is 3. So if we wanted to list out the ordered pairs, we could. I'm good with this. I'm just going to make a quick little note here. The green is the vertex matrix. The red is the translation matrix, and then what that equals is R prime, oops, let me go back to orange here, R prime, S prime, T prime, U prime. That gives us our new image. Okay, so there's translations. The next type of transformation, and I forgot to slide that back up, is a reflection. A reflection matrix is a 2 by 2 matrix that multiplies with the vertex matrix to reflect an image over a line. Now, when we write this, we always have to multiply this in a specific order, and it's the reflection matrix times the vertex matrix. Okay, it has to be in that order, otherwise it might not necessarily work. Now, there's 3 lines that are generally the lines that we reflect over. We've got the x-axis, the y-axis, and then the line y equals x. If we want to multiply, or if we want to reflect a matrix over the x-axis, what we're going to multiply by is a 2 by 2 matrix is 1, 0, 0, -1. If we multiply our vertex matrix by this matrix right here, this will reflect the image over the x-axis. If we want to go over the y-axis, what we're going to multiply is this matrix. It's -1, 0, 0, +1. So these first two just kind of switched elements there, the top and the bottom. If we want to go over the line y equals x, we're going to multiply by the matrix 0, 1, 1, 0. So it's a little bit different. Okay, these are the 3 reflection matrices that we're going to use to reflect over a line. So reflect RSTU over each of the 3 lines. Now I'm going to rewrite RSTU on this screen just so I don't have to slide back and forth. RSTU was 3, 2, 7, 4, 9, 8, and 5, 6, just so we have that, just so I have that for my reference when I write this out. So what we're going to do is we're going to take these reflection matrices and we're going to multiply it by the original matrix, the original image, and we have to do it in the order of reflection matrix times this, because if we did it the other way, it wouldn't fit. This is a 2 by 4 times a 2 by 2. The inner 2 numbers don't match. But if we do 2 by 2 times a 2 by 4, then it works. Okay. So for the x-axis, we're going to take our reflection matrix, which is 1, 0, 0, -1. So we're going to have 1, 0, 0, -1 times our image matrix, or our vertex matrix, 3, 2, 7, 4, 9, 8, 5, 6. And you can use your calculator here. At this point, we can kind of streamline the process just a little bit to kind of make things go faster and to make this video go a heck of a lot shorter. When we multiply this, these 2 matrices together, what we get is the following. In the first row, 3, 7, 9, 5, it doesn't change. The bottom numbers, they do change. They become -2, -4, -8, and -6. And that should kind of make sense. If we're reflecting over the x-axis, so if I were just to quick draw a picture here, if I'm going to reflect something in the x-axis, it's going to go from above the x-axis to down below. The x-coordinate did not change. It's still on that same line, but the y-coordinate flips sign. That kind of makes sense, but mathematically with a vertex, this is how it happens. Okay, and you can kind of check yourself thinking about it that way. If we want to reflect over the y-axis, again, we're going to use our y-axis reflection matrix. Let me go back and check that out. -1, 0, 0, -1. So -1, 0, 0, 1 times our vertex matrix, which again, 3, 2, 7, 4, 9, 8, 5, 6, and again, you can use your calculator here, make things go faster. If we're reflecting over the y-axis, what's probably going to happen is the y values are not going to change, and then the x values change sign, because again, if we're going over the x-axis or the y-axis, that's this way. We're not moving anywhere horizontally or vertically, we're just changing the horizontal coordinate, and that's exactly what happens. The x values all flip sign, -3, -7, -9, -5, and the y values all stay the same, 2, 4, 8, and 6. Now, if we want to reflect over the line y equals x, this one's a little bit different. We're going to still use our reflection matrix, but this time we're going to use that third one, so it's 0, 1, 1, 0. So 0, 1, 1, 0 times our vertex matrix. One more time. 3, 2, 7, 4, 9, 8, 5, and 6. Again, use your calculator. Make this go faster. What you get here is this. We get 2, 3, 4, 7, 8, 9, and 6, 5. So when we reflect over the line y equals x, what really happens is my x's and y's switch places, and that's common, kind of some common knowledge. We've talked about that with inverses. Remember, inverses are reflections of each other over the line y equals x, and this kind of just kind of solidifies that. So it's something you've kind of seen before, but not necessarily in this context. The third type of transformation, we didn't talk about this one in Algebra 2, but you probably talked about it in geometry, and that would be the idea of a rotation. A rotation matrix is a 2 by 2 matrix that multiplies with the vertex matrix to rotate an image around the origin counterclockwise. And just remember, counterclockwise, if we start at 12, we work our way backwards when we think about the clock. So we go from 12 to 11 to 10, as opposed to clockwise, which we think about a normal way a clock moves. Counterclockwise is the opposite direction. If we're talking rotation matrices, just remember it's the same order: rotation matrix times the vertex matrix. The 90-degree rotation, 90 degrees counterclockwise, is 0, -1. Oops, not -1 again. It's +1 and then 0. If we want to rotate something 180 degrees, it's another 2 by 2 matrix: -1, 0, 0, -1. If we want to rotate something 270 degrees, we're going to go 0, 1, -1, and 0. Okay, so those are our three rotation matrices depending on which direction we need to go. All right, so let's talk another example. ABCD has vertices there. You can see them rotate ABCD about the origin. We're going to go 90 degrees, 180, and then again with 270. So if we talk about 90 degrees, we're going to go back to that 90-degree rotation matrix. So 0, -1, 0, -1, 1, 0. Times, and we need to make a new vertex matrix because now we've got a different image. So our A is 1, 1, -1, 4, -2, 4, and -2, 3. And again, use your calculator here, type these in, get your reflections, or not your reflections, your rotations in there. What happens when you do this is your new vertices become -1, 1, -4, -1, -4, -2, and -3, -2. If we wanted to rotate it 180 degrees, we're going to use the 180-degree vertex matrix, or the 180-degree rotation matrix. So that's going to be -1, 0, 0, -1 times our vertex matrix. We just created that: 1, 1, -1, 4, -2, 4, -2, 3. And when we type these in our calculators, do these two matrices, multiply these two matrices together, what we get is -1, 1, 1, 4, 2, 4, whoops, don't need a fraction bar there, 2, 4, and 2, 3. And I just did it again, 2, 3. Kind of hard to break that habit. So there's our 180-degree rotation. 270-degree rotation, go back to that third rotation matrix: 0, 1, -1, 0, 0, 1, -1, 0, times our vertex matrix, which is 1, 1, -1, 4, -2, 4, -2, 3. And one more time in the calculator, what gives us a result of 1, -1, 4, 1, 4, 2, and 3, 2. And there is our rotations of 90, 180, and 270. If you wanted to graph to make sure, feel free, but I'm more focused on getting the points rather than putting points on a graph. I'm pretty sure you can do that by now. The last type of transformation is a dilation. You probably talked about these in geometry as well. We kind of talked about them in Algebra 2 a little bit. We called them stretches and shrinks, but it's basically the same thing. Dilations are definitely the easiest. It's simply scalar multiplications, and it will give you the scale factor, and that's the number that's going to go out front of your vertex matrix to get your new image matrix. So parallelogram WXYZ has vertices. You can read them there. Find W prime, X prime, Y prime, Z prime for a scale factor of 1.5. So what we need to do is we need to make a vertex matrix of WXYZ. So we'll have -2, 4, and then we'll have 0, 8, and 4, 6, and 2, 2. There's our WXYZ, and we're going to take that times our scale factor of 1.5. That's going to go out front, and this is distributive property. Just like with scalar multiplication, we're going to take the number on the outside times every element on the inside, and what we get when we do this is -3, 6, 0, 12, 6, 9, and 3, 3. So what that does, it makes all of the original side lengths from here to here, here to here, here to here, and then the last one back to the first one, it makes it 1.5 times longer than original. And that's what a scalar does. That's what a dilation does. It makes it long, makes the sides longer or shorter, and it's in reference to the origin.